Welcome everyone for attending our Lockheed Martin Mellon Robotics Center seminar series. Thank you again to Lockheed Martin for their continued support of our seminar series. I'm very excited for our seminar today. Our seminar speaker is Professor Hsieh. She's an associate professor in the Department of Mechanical and Applied Mechanics at UPenn. She's also the deputy general of the deputy director, of the GRASP lab and the program chair of the Robotics MSc program. So for personal note here, I'm in some sense a GRASP alum. I did my postdoc at GRASP lab, and my advisor did his PhD at GRASP lab. So I'm have a fond connection whenever we have speakers from GRASP come and speak in our seminar series. Ani works in a very interesting intersection of robotics, multi-agent systems, and dynamical systems theory. I've always been fascinated by the papers that come out of her group. Her team has designed several algorithms for estimation, control, multi-agent robotic systems, in particular with a focus on estimating, monitoring, and predicting complex dynamics. Some really cool work there. Before she moved to Penn, she was a faculty at Drexel University for a few years, where she led a very robust program. She has won several awards, including the ONR Young Investigator Award and the NSF Career Award. And I've always been a big fan of the research that comes out of her group. I've always looked for papers at HICRA or IROS coming from her group, because it's always very cool intersection of deep theoretical mathematical insights with a very strong application in particular to marine robotics, something that I'm particularly interested in. So it's my pleasure to have Professor Ani Hsieh speak to us. Ani, take it away.
Thank you so much for talk. That was, thank you so much. I'm so, this is a little embarrassing. That was, thank you so much for that introduction. I'm so humbled. It's great to be here. I apologize for not being there in person. But the great thing about one of the great things that we've learned about this pandemic is through this remote setting, we can really close that physical distance, right? So please feel free to interrupt me, put your questions in the chat. I think Pratap and I just talked about how I should be able to feel free to interrupt. I'll try to keep an eye on the chat, and let's go from there. So because I'm part of the job of being deputy director for GRASP is that I am program chair for the Robo-MSc program. And so, because of that, I have to make sure that I put in a plug. So just to give you a quick overview, right? So GRASP is this robotics incubator. We like to think of ourselves as the center that really fosters collaboration, right, between students, research staff, and faculty, really focus on the fundamental research and vision, perception, control systems, automation, machine learning. So anything that you can fit under the umbrella of robotics, basically we do. The GRASP was established in 1979 by Dr. Rujina Fachi. So Rujina is actually back at Penn. So she's now a fellow in the School of Engineering. So it's great to be able to see her. And it is, so GRASP is primarily housed in the School of Engineering and Applied Science. We now are about, actually my numbers are a little off. We now actually have 20 primary faculty. We're spread out across 3 main departments, mechanical engineering, electrical and systems, and computer and information sciences. We have right now about 10 affiliated faculty. This is a new program that Mark and I had started, and that was initiated by previous directors. And this is really bringing in researchers at the University of Pennsylvania that does anything related to robotics. So we not only have faculty within the School of Engineering, but we have faculty from School of Medicine, School of Nursing. We have people from School of Architecture and Design. We have faculty from the philosophy department. And so a lot of these very exciting initiatives, right, really is coming from this great group of affiliated faculty. So just to give you a rough sense, our PhD students, we have about 130 plus PhD students. Our robo class is now about 180 students spread out across 2 years. And then we have roughly about 19 research staff, and this includes both specialists, scientists, and postdoctoral researchers. Just when I go out and do my recruitment talks, I sort of like to, the way I describe it is like if the robot walks, if the robot swims, if the robot drives, if the robot flies, we do it all. And so this is our current snapshot of the wonderful faculty, the primary faculty within this area. And so if you look at this, we actually cover a lot of different research topics and focus areas, but it's not just the fact that we have good coverage, we actually have really nice intersections, and so that sort of allows us to have this very, very collaborative atmosphere. So having said that, let's talk a little bit about what my group does. So my group, really, we're sort of very much focused on thinking about large-scale monitoring, sort of large-scale, smart, adaptable sort of sensing networks. And predominantly, we're really looking towards this from an ocean monitoring perspective, right? So really this goal of sort of being able to develop a large-scale, smart, adaptable network that consists of both static and mobile sensing platforms, okay? And so the idea here is this heterogeneous sensing network, right, would include existing satellites, surface, static and passive observational platforms, as well as autonomous aerial, surface, and underwater vehicles. And the idea is really thinking about all these platforms, right, to be able to use them in a cohesive fashion so we can achieve the continuous and persistent sampling of the ocean, and that in such a way that we can continuously fuse multi-resolution data into this consistent description of the environmental dynamics, right? And there's, obviously there's a good reason why we're interested in doing this. The ocean, right? The surface of that ocean covers over 2/3 of the Earth's surface. It is the primary driver of climate weather patterns across the globe, which means that anything that happens in the ocean has a direct impact on our life on land. So I usually like to hold out my cell phone at this point and then say, think about all the things on you. So, your clothes, your cell phone, your watch, your jewelry, all of these things that you use and come into everyday life, at some point, most of those things or some component of those things have actually spent some time on a boat or on a ship, okay? And so so we cannot emphasize, right, sort of the importance of the ability to be able to think about not just, monitoring, but also thinking about how, part of the reason why we want to do this monitoring so we can do a better job of doing prediction and then be able to translate all this data into good decision making, whether it be for sort of weather forecasting, whether it be for sort of search and rescue, for contaminant dispersion and sort of mitigation purposes, cleanup. And these days, right, the big term is about coastal resiliency, right? So how do we think about making sort of our infrastructure on land to be more sort of resilient to severe weather systems, okay? And so basically, given this sort of idea, my group actually works, we think about this idea of, using all this sort of big, large network, right? And then be able to think about how do we control all these different sensing platforms, right, in such a way that they are continuously adapting the locations where they're collecting data, and hopefully be able to do this in an on-demand fashion, because the point is you're trying to continuously improve the quality of the data that you're collecting. Because you're improving the quality of the data that you're collecting, all of this data can get then assimilated and updated into your models, and effectively create this virtuous cycle where high quality data leads to higher quality models, which then leads to more effective sampling strategies. So because of this, we work sort of everywhere along this cycle. So everything from planning, control, coordination of these teams of static and sensing platforms, We think about developing estimation algorithms that allows us to fuse and assimilate this data into a consistent representation of the environmental dynamics. We think about, what are the best ways when we think about representation, when we think about models, right? What is the right way to capture, and build these models in a way that not just gives us good fit to the data that we've seen, but also good predictive power, okay? And then, of course, we also think about new sensing platforms, and I'll talk a little bit, hopefully towards the end, about sort of how do we redesign, right, our mobile sensing platforms to be more energy efficient, to better interact with this very dynamic environment, and how do we think about leveraging the dynamics of this environment to help us do more energy efficient control and navigation. So today I'm just going to sort of focus on I would say this is a representational component as well as the sort of discovering dynamics component. And I'm going to sort of focus on this sort of one line vein of work that, my group has been doing. And, one of these, so today, if you do robotics, it's almost impossible for you to not do machine learning. And so, this is, so we're going to talk a bit about machine learning, but we're going to sort of talk about in this context of trying to learn complex dynamics, okay? And so one thing that we sort of stumbled upon as we were sort of trying to do some of this work was this neuro-ordinary differential equation framework, okay? And so this is this learning framework, and I'm, people who have done perception and vision are probably very familiar with neuro-ODEs. And this idea about how does one sort of reduce the complexity of the learning framework, right, sort of by taking advantage of this variational formulation. So what do I mean by that, okay? So neuro-ODE sort of, the way they think about this is, you have some observations of state. These are time series data. And this time series data you assume, right, is sort of the result of some dynamics, okay? And in this particular case, we're going to start with the assumption the dynamics is sort of evolves based on some kind of an ordinary differential equation, or the fact that you can describe the evolution of that state through some kind of ordinary differential equation. And really the objective here is about how can I somehow, right, come up with a data-driven sort of representation of this dynamics model, okay? So really thinking about coming up with an estimate for F hat in this case, right, or the vector field, okay? And so oftentimes I can think about this, I'm going to think about this in this context, in the neuro-ODE context of thinking about the representation using this neural network or some kind of a learning network. So the nice thing about this nodes framework is really the fact that, when you think about the way they construct this learning framework is you say, well, then now what I can do is I can sort of specify this loss function. And now this loss function, right, is simply going to be, require me to, given the current observation that I have, if I have an estimate for the dynamics, then really I can now do forward propagation, right? So I can think about prediction by simply doing a numerical integration, right? And so this really just requires us to run a sort of ODE solver and pick your favorite. If you want something easy, that'll be Euler. Standard, pretty standard stuff is Runge-Kutta grade 4, the fourth order Runge-Kutta. So pick your favorite ODE solver, and then you have this way to essentially figure out what the loss is going to be in some future time, and then you can then compare that with another observation, and then now you can think about minimizing the difference between your observation and what your network is really predicting. And so through this, so they formulate the optimization problem, right, through this variational framework, and it's effectively it just becomes sort of this, this Lagrangian approach by doing this optimization, where now you have these, two-state boundary value problem, where part of it is you need to solve your state equations. And then you have to solve your co-state equations backward in time. And then you have a way to express the loss in terms of the parameters of your neural network. And in this way, you now have a way to think about optimization, okay? So The reason why we like this framework so much is the fact that it actually, because of this variational formulation, it actually makes embedding first principle knowledge of the physics of your system very, very natural and very straightforward, okay? So basically, instead of so I can think about observations along a trajectory. Okay, so that's the blue, that's my sample trajectory. I have an estimate, or I have a prior for what I think the dynamics is, and that basically is my neural network. And then I can just sort of, through numerical integration, I can sort of integrate things forward in time based on the current observation that I have and the current estimate of the dynamics. And then the optimization problem is really about minimizing, right, sort of the error between sort of at some future time between the true, right, and the predicted, okay? And within this variational framework, so the loss function, basically you can think about this as just minimizing that error. I can think about, right, so if I know something about the dynamics, I now have a way to constrain, right? So I can add the quality constraints. If I knew something about the initial conditions, right, I again have the ability to add those additional constraints. And then again, within this framework, now this optimization, so this is this idea. This is my dynamics. I'm trying to estimate, right, what the dynamics of the system is, but I have some prior knowledge. And this prior knowledge can be data. It can be equation in the form of an equation, because if it comes from the equation, they actually can be very easily embedded within this neural ODE framework. And then, of course, I have the parameters of the network that I'm trying to optimize over. And so in this way, we can come up with sort of this blended view, right, this hybrid representation of the dynamics of the system, where part of you have your knowledge, which is F tilde right here, and then you can have the neural network, which is making up for the difference between what is known and what is not known. We have this blending matrix where the parameters are part of the parameters that we're trying to optimize over. And then at the end of the day, you can sort of formulate this, as a variational optimization problem. And really the steps are pretty straightforward, right? So by doing this optimization and applying Lagrangian multipliers, you now have the ability to come up with two sets of equations, right? It's a two-point boundary value problem. You have to solve the state equations forward in time. You have to solve the co-state equations backward in time. All of that is simply a numerical integration. And then you have a way to come up with a closed form description for the gradient, right, of your objective function with respect to the parameters of the system. So this is why we love this framework, okay? So here's a couple of things I wanted to comment about, okay? So neural ODE, I would say that it's part of this spectrum of these scientific machine learning sort of frameworks now that are becoming more and more popular and are getting a lot more attention, right? And so the idea here, the reason why that particular community, they call this scientific machine learning, because it's not really just thinking about this black box learning problem, but really thinking about how do you blend, right, sort of these state-of-the-art machine learning techniques with sort of first principle knowledge in terms sort of this mechanistic approach to sort of doing modeling that we've been, learning, since in high school, if you do physics, right, sort of all the way up to graduate school, right? So these very first principles approach to doing modeling, okay? And it's really about how do we merge the two together. So one thing that I will comment, so, common techniques that you guys most likely have not heard of, I think the most common is SINDI, right? Entropic regression, SINDI, and universal diffuse. I would sort of classify them under this umbrella, where oftentimes you have to know a lot about the fundamental physics, right? So for example, like entropic regression and SINDI and universal diffuse, most often you're relying on some library of basis functions, and you're trying to figure out which of those basis functions, constitutes, right, can, best approximate the model, right, come up with this approximation model that best fits this data that you have. And the outcome, right, of those techniques is literally a set of equations, right? It gives you a set of differential equations that describe the dynamics of the system. Now, in the middle, so this is sort of closer, sort of somewhere in the middle, is these new systems, these new frameworks that are these Hamiltonian symplectic SimNets and Lagrangian neural networks. They're all very similar, right? They really mostly apply for reversible systems, and these are sort of, this takes a very dynamic systems point of view, right? So they give you some ability to encode priors, like known equations, but again, it's very limited for a small class of dynamical systems, okay? And of course, there's things like RNNs, as well as, so RNNs here, but the problem, of course, is, RNNs fundamentally, you're looking at trajectory data, and you're trying to extract vector field information. And so there seems to be this disconnect as to where sort of along, what your observation is compared to what you're really trying to learn. And so it makes, imposing continuity constraints and smoothness constraints somewhat difficult. I'm throwing here these graph neural networks only because, a lot of the work in swarming on learning controllers for swarms have been posed in this sort of imitation or reinforcement learning context. And then what you see when we do it within this, knowledge embedded neuro ODE framework, it's actually a little bit different. So we actually don't need to know, right, what an optimal set of behavior is, because we're moving away from this imitation learning strategy. So just to give you a sense, this is a part where it's now all fun, hopefully. And so let's give you a sense of the kinds of systems that this framework is particularly well suited to be able to learn the dynamics for. Okay, so I'm just going to show you. So the ground truth equations are shown at the very top, and this is your general hot normal transform. The system parameter mu here, so mu below a certain amount, right? So you end up with a single attractor. Okay, this is this. So we actually trained this system with 3 trajectories, and the trajectories are shown here. And the other thing is the dark part of the trajectory is t equals to 0, and it becomes lighter as t goes to infinity. And so what you're seeing here is sort of 3 sample trajectories. When mu becomes larger than 0, you end up with the single attractor, sort of experience this bifurcation, and then you end up with the limit cycle and in sort of a limit cycle instead of the attractor. And so using this neuro ODE framework, what you can do then is not only do you learn the dynamics, you now have the ability to sort of interpolate what the resulting dynamics is going to be for different values, right, of this parameter mu, okay? Another example, so this is a stiff differential system. We purposely picked the parameter mu for this van der Waals to be in the stiff regime. And so these stiff problems are especially difficult to solve because, you end up with, this different sort of rates. In some things happen slower, other things happen really quickly, and you end up with not a lot of data, right, during the regime where the process, when things happen very quickly. So these becomes really hard numerical problems to solve. And so here again, we have our, training data set, which is shown in red in this panel, and then the model prediction shown in black. In the right-hand panel, it's a little different. So ground truth is on top, and this is just, extrapolating, allowing the model to extrapolating beyond the time frame of the training data set. And what you're seeing is the fact that we're actually doing a really good job of learning the dynamics, even when the problems are, numerically challenging, okay? So this is, for us roboticists, you're looking at this as like, oh, well, but, these are relatively easy systems, right? And it's like, yes, they're actually pretty easy. So here's an interesting one, okay? So let's so one question is, we're often, when you look at the swarming literature, right, the objective is really how do you synthesize single agent controllers such that at the collective level, you actually end up with something interesting, right, at the swarm level. How do we design single agent robot controllers that really only, sort of operate on local information and then be able to get some kind of a cohesive motion pattern, right, at the global level. This kind of shows you, so when I say this, it'll give away how old I really am, but when I was a PhD student, right, like we would spend our entire PhD time, right, working on coming up with a single agent controller. And then the purpose of the PhD is to show that the single controller actually does what it's supposed to do at the swarm level or at the ensemble level, right? And that fundamentally is a very hard problem, okay? So here's what we want to do. If I have the ability to make observations, right, of the swarm trajectory, so now I'm really thinking about if I can actually observe the individual states of the elements in the swarm, okay? Is there a way that I can learn what the single agent sort of closed loop control strategy is, right? If I learn that and I apply it to a different swarm, the resulting swarm is going to exhibit similar motion patterns at the collective level, okay? And so here's what we're going to do. We're going to pose this as this system ID problem, and we're going to make assumptions about the open loop dynamics of the single agent. We're going to make certain assumptions of how that single agent interacts, and then we're going to sort of, make assumptions on sort of how obstacle avoidance and collision avoidance is handled. And the hope is that, because these things we can embed as knowledge, then we can figure out, right, the output then is a controller that we can then sort of run on a different agent, part of a different swarm, and hopefully result in the same swarming behavior, okay? So this is kind of this idea. So we have some idea, we have notions of cohesion, alignment, and separation. This is basically just the Reynolds-Boyd simulation in 3 dimensions, okay? And so this is ground truth. This is a team of 10 agents. And so that's kind of, and here's the idea within, so one thing to note, so I'm going to spend some time talking about this. So one thing we did is that so we used the Boyd simulation to generate training data, and then we used this KNODE framework, this knowledge embedding with neuro ODEs in order to learn that single, the controller. So, and then we applied it to a different swarm of the same size, okay? So this is, we learn from a swarm of 10, so then we apply it to a new swarm of 10. And so here what you're seeing is the energy distribution of the principal component elements. So these are the principal dynamic modes of the system, of the swarming system as a whole. So ground truth is shown in purple, and then green is shown, the green is showing the sort of learned dynamics, right, from this model. And you want to have good correspondence in the sense that the shape and the distribution of those sort of eigenvalues, right, associated with each of those dynamic modes, you want them to have the same shape because that is actually implying that you're capturing the right set of dynamics, okay, at the swarming level. And so this is what we're showing is that, yes, you can actually learn the swarming dynamics. Here's the other interesting thing. We just kind of plotted this because we were just curious. And this is really about the algebraic multiplication of the 0 eigenvalue for the graph Laplacian. And it's really just trying to measure, within the swarm, how many of them are sort of, within each other's communication range, how many subnetworks that it's forming, disconnected subnetworks, because that happens sometimes. And so again, orange is the ground truth, and then the blue or the light purple is the predicted or the learned model. And we're seeing this really, interesting, correspondence. It's obviously not one-to-one, but we're seeing some interesting correspondence here. Here's the really cool stuff that I think, and hopefully I'll get this to play. I think I have to switch this up for a second. Turn this off. Okay, so let's take a quick look here. So the first video, this is again showing you sort of the ground truth. The cross in the middle, that is basically the center of mass for the swarm. And then the learned model is shown in blue. Okay, so this is again a group of 10 agents. Here's what is really cool is now you can take the learns for that group of 10 agents and apply it to a group of 40. And so what we're showing is we have this ability to generalize, right, to effectively generalize to different initial conditions of this ODE system that you've learned, okay? And then you can sort of, again, so then we scale it up to 50, and then we basically plotted the ground truth version of 50 agents compared to the blue one, okay? And so a few things to observe. First of all, they don't necessarily, sort of from a dynamics perspective, we're capturing the right side of dynamics, but from a motion pattern, so we're sort of roughly seeing similar motion patterns, but that doesn't mean that the individual trajectories will always match up. Okay, so that's the one thing to keep in mind. The other thing is that you're seeing some jittering that's going on when we're applying this learn strategy to a larger team. And part of this is because we're confining the swarm to the same workspace. And so when you have, the more agents you have, the more you have to worry about collision avoidance, and some of those numerical issues start coming into play, and eventually things do blow up because you just essentially have way too many agents within this confined workspace that we're in, basically. Okay, so this is kind of neat. Okay, so let's move on. Okay, so here's another example. So this example, oops, sorry, let me go back. So this is this deformable image registration problem. And I'm just gonna sort of throw this out there. I know nothing about medical imaging. It just so happens that, my graduate student Tom happens to be roommates with Yufan, who is the graduate student of James G, and they started talking, and voila, we have this awesome paper. And so apparently, this problem is particularly well suited for this nodes, this neuro ODE framework. And the idea is, how can we extract the map, right, sort of the deformation map effectively, that sort of can convert, right, that when you apply it to the pixels on your sort of moving image, and then transform that into this other image, okay? And because of this is a problem that has a lot of, you impose a lot of continuity and smoothness constraints. And so because of this, it works, the nodes framework actually works extremely well for this. Existing approaches, right? So there are sort of these first principle derived approaches, which is this LDDMM approach. So these are unfortunately, these techniques are slow. And so the advantage of having a learning-based strategy is really about improving the time it takes for you to be able to compute that transformation map so that you can, do things like faster inference and then see, and make sure that you can do diagnostics and things like that, okay? So here's an example of our, technique. And so if you look at this is just showing you how the transformation map that we get using this KNODE framework, right, is really preserving some of these, smoothness and continuity constraints. And so what you're seeing is everything is all, even if you started with sharp corners, you always end up with rounded corners, no matter what sort of final shape you're trying to get to. And it does not violate topological constraints as well. So the donut, even though we're trying to get the donut to turn into a sphere, the sphere is never a true sphere because you always have the hole in the middle. And the same idea here, you have two disjoint sets. You're trying to sort of transform them into a sphere, but you're always going to have this boundary in the middle between the two. And in fact, what we're seeing is the fact that sort of, if we look at the nodes formulation, there are certain types of smaller features we do particularly well when we actually do preserve these things, okay? So there's a couple of questions here before I move on to the next example. And so one of the questions is, did we learn a model using observations from one or more agents? We learned the model assuming we had observations for all agents in the swarm. So that obviously is potentially not a very realistic assumption, but we can talk about that towards the end. I have some ideas about that. I'm not sure if you already mentioned it, but how did the node-based swarming system compare to reinforcement learning? Unfortunately, we haven't done compared it to a reinforcement learning strategy, and so this is something that my suspicion is we will probably generally will do better because we have the physics to constrain the learning, and therefore, in general, we will require less data for training. Okay, and that's only because you have knowledge, right? So that's not so surprising. Let me just check the Q&A real quickly. How do you select the training trajectory set for a nonlinear system? Does it guarantee globally convergence, converge to the ground truth? Those are good questions. Right now, we're basically trying to learn, right, a single trajectory. Let's talk about that a little bit because I want to come back to that. There is a difference between learning the dynamics around a particular solution versus learning the dynamics for a particular sort of area. And I think that really is a great question because it really talks about what training data you need. Okay, so let's come back to that. Okay, let me go to another example. So here's an example for the model predictive control. We all know we love model predictive control because this is a great way for us to be able to do good controls. There's a lot of nice results from a sort of from guarantees perspective, right? And this is a very common strategy. Fundamental to model predictive control is that you need a model, okay? And if your model's not very good, then that's potentially really problematic, especially if your systems are fundamentally unstable, right? So here's what we did. We sort of picked a quadrotor, and so we used the full-blown dynamics model of the quadrotor. So this is about, let's see, this is 14 states, right, and then 4 inputs. And so here's the dynamics so let's assume that the dynamics of the quadrotor, so we know a lot of the dynamics, which is fx comma u. But then we have sort of essentially residual dynamics, right? And this could be because of disturbances. It could be because you didn't quite get the, capture all the aerodynamic effects at the different speeds that you're flying at based on the trajectory that you're trying to track. And so these disturbances so those are your nominal dynamics, right? And these are sort of uncertain residual dynamics or even poorly understood dynamics, okay? So stuff that you have an idea what's causing the effect, but maybe you don't know it exactly. So, so here's what we did. We basically used, so we have our quadrotor that's, described by our nominal dynamics, where you're going to use in your ODE to capture the uncertainty or the residual dynamics. And essentially that's our KNODE model. And then what we're going to do is we're going to throw it into an MPC controller. Okay, so here's our KNODE model. And then we're going to use that model to compute the control input and then apply to the quadrotor. And then we're going to feed the states back and essentially recalculate, right, what the control is going to be. And of course, this is assuming the quadrotor is trying to follow a particular desired reference trajectory. This is a little hard to see. So you kind of have to squint at it a little bit, but eventually you see this little blinking light flying around. The video on your left-hand side, this is just a simple quadrotor flying around a circular path, okay? And so we used a very straightforward sort of geometric controllers to get it to fly around the circle. And then the KNODE-MPC controller is running for the quadrotor in the video that is on your right-hand side. And what you're seeing here, let me play this and there we go, let's play this again. So the bottom panel, where you're seeing is the fact that the horizontal line is actually showing the radius of that circle. And so in general, because we can really capture those dynamics, right, those residual dynamics really well, and we're doing a much better job of tracking, right, that circle and following that circle. And even went outside of the speed ranges that we, sort of trained the system at, okay? So it does nicely. So let's take a short break here, and so I'm sort of towards the end of my talk. So I want to make sure we have time to answer questions and discuss. So, this is this KNODE-MPC framework, okay? And I'm telling you, so I started the talk by saying, well, I'm interested in building sort of these big observational frameworks, right? And I sort of gave you this example of this learning framework that if I can somehow, I have this ability to incorporate physics and essentially constrain the learning, right? And really focus on learning stuff that I don't know, right? And I gave you some examples of systems whose dynamics are governed by ordinary differential equations, both sort of low dimensional as well as high dimensional systems. It seems pretty neat. So how does this relate, right, to this idea, okay? So one thing to keep in mind is that, right, it's the ocean is really big, and instrumenting the ocean can be very costly. And so what we're saying is that what we do not want to do is effectively think about a strategy that blankets the oceans with sensors, because not only is that economically infeasible, it's just ecologically unseemly, okay? So instead, what we want to do, right, is really about large-scale modeling. We want to focus on sampling. We want to focus, right, on sort of the kinds of constraints we have to operate with, right? And so oftentimes that means that it's a big space. I don't have a lot of sensing resources, which means whatever sensing resources I'm sending out, I really got to make sure that they're out and being very effective as to where they collect data, and that the data that they collect and that they bring back is going to be informative, okay? Oftentimes, especially if you're underwater, you're working with communication constraints, right? And therefore, we have to take those kinds of constraints into account. But really, the idea is about how do we do this, right, sort of achieve this vision while simultaneously doing this in a way that makes the most of what we have, okay? And so when I'm thinking about this KNODE framework, I'm actually not really thinking solely about how do I improve the dynamic model of the robotic systems that I have, right? I'm not just thinking about that context, but I'm really thinking about how do I really think about using this framework to learn even more complex dynamics that has variation in both space as well as time, dynamics that is subject to high uncertainty, dynamics that is oftentimes, right, can be, you know, that has, in the ocean, you have things like turbulence, you have chaos, right? And so how does this framework, right, how can we leverage this framework to solve some of those problems? And here's sort of the reason why that, I think, is a really important problem, okay? So one thing that we know is that when you operate assets, right, your robots in environments like the ocean and the atmosphere, we know the fact that the dynamics of those environments is essentially coupled with the vehicle dynamics. But if you think of it, so this makes this control problem very, very hard. But it's actually, for every challenge, there's an opportunity, right? We can think about the ocean, we can think about the atmosphere as this sort of infinite energy reservoir, right? So it's a reservoir that gives me infinite forces, but I need to know how to leverage that force so that I can do a better job from a control, planning, and deployment perspective. And so people are doing that, except for the fact that, you know, people have said, well, can you know, leverage ocean currents to be able to come up with minimum energy paths for vehicles operating in these kinds of dynamic environments? Yes, you can. But fundamental to that work is this assumption that I have the ability to get good quality ocean current data, which is very, very hard to do, okay? Especially at the spatial temporal resolutions that actually will make a significant difference to the robotic platforms that I'm working with, okay? Which then means that really I need to have better ocean models, right? And so how does this, you know, sort of contribute? How does our KNODE framework contribute to this, okay? So of course, you know, we have things like, you know, how do you deal with communications and things like that. I'm going to skip this real quickly because this real slide was really just showing, so this is a great example of a spatial temporal process that actually has different spatial as well as temporal scales, and how you know, when you have heterogeneous sensing assets, you can actually do a better job of reconstructing what the field is, the dynamics of the field, because you have the ability to get high resolution data as well as low resolution data. But I'm not going to sort of spend too much time on this because I want to make sure we have enough time at the end. But here's this idea of learning chaos, okay? So I'm going to use this knowledge embedding neuro ODE framework. And then I'm going to make this claim that not only can we learn systems, right, that are governed by ordinary differential equations, I'm going to see if I can now learn systems with ordinary differential, sort of governed by ordinary differential equations that are fundamentally have chaotic dynamics, okay? And so here's what we're going to do. This is your Lorentz sort of system. It is fundamentally, this is a chaotic system, you know, given the right set of system parameters. And this is just an example of one trajectory of this Lorentz system, okay? given this trajectory, this is what I threw this trajectory into Cindy, which is why the coefficients look kind of funny, okay? And I did something that, not quite fair to Cindy, okay? So we purposely did not include the right set of nonlinear terms in the library when we try to extract the equations for the system. And so the resulting sort of solution for the system that we sort of learn using Cindy is shown here in the bottom right, okay? So one thing to note is that when we apply the 0-1 chaos test, 0 being the fact that the system is not chaotic, 1 for the system being chaotic, the resulting learned dynamics for the system is not chaotic. So we obviously have captured the wrong set of dynamics for the system, okay? I'm not going to go into, we have references about this metric that we're using, but here's this thing. This is one of the cool things that we've been able to show. So again, here's my training data set. This is a trajectory for that Lorentz system between 0 to 8. The knowledge was the set of equations that I showed you in the previous slide. And now we threw this into our KNODE learning framework. And then we asked this learned framework, the learned model, to extrapolate the dynamics of the system, from beyond the time that the training data set. And when you actually apply the 0-1 chaos test, what you're seeing is the fact that our KNODE model not only has the ability to compensate for the incorrectly learned dynamics from the previous system, right? But we are also capturing a fundamental property, right, of the original system, okay? And so this is the part that is extremely exciting for us. So what does this mean, right? So here's another example. So this is a one-dimensional chaotic PDE. So this is a system governed by a partial differential equation. This is called the Kuromoto-Shibashinsky model. So the spatial coordinates is actually plotted along the vertical axis. The horizontal axis is time, okay? And then the time, we kind of scale it in terms of Lyapunov time. So the Lyapunov time basically captures the sort of, the usual relaxation time for the system, okay? So that's kind of one way to think about it. So here's our training data set. Of course, there's the testing data. We then did model prediction for the spatial locations where we didn't have the training data. And then this makes no sense, but I'm going to just explain why we did this, okay? We took the difference between the model prediction, right? And what we're seeing is the fact is that, so this is a chaotic system. You do not expect, sort of, you wouldn't expect good correspondence as time increases over time, right? But what is really cool is that this is before we even incorporated the knowledge element, we're already getting 4 Lyapunov times. We're actually doing a pretty good job of capturing the dynamics within the first 4 Lyapunov times. So based on this and some of the preliminary work that we've done, we believe that once the knowledge becomes embedded, you potentially now have the ability to do better. And I would say that sort of state of the art for this particular test case, right, this Kuromoto-Shibashinsky model, is about 6 Lyapunov times with knowledge already embedded in it. So even without knowledge, we're getting up to 4, okay? So here's the part, so, and then here's the POD, the energy scatter plot for the eigenvalues with the associated dynamic modes of the system. And we're seeing that we're actually getting, most of the dynamics, the distribution, okay. So here's kind of where we are, right? So given some ocean data, okay, and then you told me, okay, this is where this rubber ducky, and I'm purposely picking a rubber ducky because it's not active, okay, it's a completely passive element. Would I be able to tell you exactly where along the Gulf of Coast, where along the Gulf of Mexico, which coast, right, where along the coast is the rubber ducky going to land? No, I'm not promising that, right? So there's no way we're going to be able to do that, at least not right now. But here's possibly what we will be able to do hopefully real soon is, given where the rubber ducky fell into the water, is there a way that we can now figure out sort of where are the likely places, right? What is the distribution of most likely places this rubber ducky is going to land? And I think we're getting sort of towards that, in that direction, okay? So I'm going to, so there are other, it's not, this is not just about point measurements. It is not just about, sort of direct observations of states, right? We want to, there is more structure to dynamics, right, than just this is the vector field at this point in the state space, but rather there are actually these large scale features, especially for nonlinear systems. And so there are these things, so we can think about the ocean dynamics and thinking about a map for that environment, right? Not only that captures the dynamics, but also think about larger features that allow us to do reasoning about the dynamics. So very similar to this idea of, mapping for, self-driving cars, for manipulation, and sort of thinking about semantic reasoning and semantic, using semantic mechs to be able to then do semantic reasoning and then do semantic planning and so on and so forth. So there is that kind of stuff, okay? So I'm just gonna stop here and I'm gonna do my shameless plug, and I'm gonna skip a lot of this because I'm running out of time. But here's really a few things. So a lot of the work that I talked about today, we're hoping everybody's gonna show up in Philadelphia towards the end of May. We are excited to host everyone and be able to see everyone in person after 2 years of only virtual conferences. We actually have a workshop on Monday that is robotics for climate change. I'm super excited about this because we're actually not just bringing roboticists, but we're actually bringing people from climate science, people with some sort of experience in being not in policy and sort of setting policies and thinking about the problem sort of in a more holistic way, okay? And then, so this is kind of, and then the talks based on the different works that we talked about. And then just to end, I want to thank, this is my group and all our collaborators. This is a really big problem. It's a really large, sort of group effort. And, we're always happy to collaborate with people who, have a passion for these types of problems and these types of applications. So thank you again, and, I'll open the floor for questions.
Awesome. Thanks a lot, Annie. I'll applaud on behalf of the audience here. Folks, if you have questions, you can type it out. You can raise your hand and I can unmute you if you would prefer asking them out directly. But I'll start it off. I really enjoyed the talk. There's a couple of questions I had. One, at some point you mentioned sort of this was trained on a swarm of size 10, and then we tested on another swarm of size 10. So what makes the two swarms different?
So it's really so the main thing was that we took the controller that we learned using the training data that was a swarming of size 10, a swarm of size 10, and then just applied it directly to a swarm of size 40. So let me see if I can bring those slides back up. Hold on, I gotta turn this off, and then let me move. Let me just hold on. And it's really so fundamentally there's the only thing basically you have your learned models, right, and then you just apply to a bunch of different initial conditions. That is really what is different. Yeah.
Yeah, so, I think that's sort of that's what
that's the cool part is that you can so this goes back to this question in that Q&A earlier, right? That swarming problem is a great example of learning the dynamics, right, sort of within some kind of a region of the state space. And the way you can think about this is that the swarm itself, right, every single agent, right, is giving you a sampling of the state space effectively, right? So this is why, and so when you get good sampling and then you have the ability to constrain the learning with knowledge, then it is not so surprising that you have this ability to learn sort of the more general dynamics, right? In the KNODE case, we're actually learning the dynamics, that is sort of around a reference trajectory. And so in that case, if you picked a slightly different reference trajectory, really it's how you can generalize that. we can do it as long as we have learning samples, but that becomes potentially a little trickier. So there is another question from Nikhil. So how does the generalization performance of the methodology compare with classical supervised learning, where train and test distributions are required to be from the same distribution? So I think, so that's a great question. At this point, we have not done super detailed analysis just yet, and this is kind of the work that's coming down the pipeline. But at this point, we're assuming that they do have to be from the same distribution, okay? And part of this, or the training, another way to think about this is that the training data set has to capture enough of the region of state space, right? For you to be able to learn a good enough, model that approximates that region of the state space. And so, so the original neuro ODE work, right? Sort of, there's the fundamental assumption is the fact that your system dynamics have to be stable, okay? With the ability to embed knowledge now within this framework that we have, now you can, because you have this ability to embed knowledge, you now have the ability to learn systems that, whose dynamics are not just, stable, you actually have sort of a larger set of dynamics you can learn. But fundamental to this is the fact that we do think that you still have this issue of wanting to make sure that the training data set and the test distributions are from the same distribution. But I think the ability to constrain the learning with that physics becomes very, very powerful in this particular case.
Thanks so much. Yeah.
Awesome. Thanks. Michael has a question as well. So Michael Roti asks, do any interesting insights into the chaos or dealing with it pop up in the models that you train to deal with the chaotic case?
So one thing to keep in mind is that in the chaotic case, one thing that we've noticed that was interesting to us when we first started was that adding noise to the training data actually ended up being very helpful. And part of this was that adding the noise was kind of, you're getting this exploration of the search space, right, almost for free. And then this idea, so we have this, when we think about, and then the other thing that we did, well, my student Tom did, which was kind of very clever, was that, since we have observations of state over time, so then what you can do is you can do this thing where instead of training it in this rollout fashion, you can sort of training this in a batch fashion where you sort of time equals to 0 gets reset every at the different points along the trajectory. And in some way you can sort of really think, it's almost like you're kind of faking having this larger, sort of set of training data when you don't really, but it's almost doing a slightly more extensive exploration of the region around the trajectory that you're interested. And so I think these were things that we at the time we were very naive about this, and so we were actually very happy to see that these things were in fact and very helpful. And because of this, I think our framework is actually quite robust to realistic observational noise. So how long did it take to develop this paper and put everything together? So I actually put together a lot of papers. So let me put it this way. It took us the good course of the pandemic to really put together the original KNODE's paper and really learn how to talk about this work to the various communities. We also kind of, we're trying to publish it in certain venues that we're not machine learning venues and some of these more dynamical systems focused places. And so a lot of it for us was really learning how to talk to that community in a way that sort of made the problem more relevant to them. So yeah, no, this and then once we had that foundation, a lot of things kind of just we were able to build on top of that very quickly. So for those of you who are graduate students, it is worth the time to take your time, get your ducks in a row, make sure you're sort of setting everything in the right place, and once you have that, you really can build on that very nicely.
Awesome. Any last question? Anyone? All right. If not, let's thank our speaker. Thanks a lot, Ani, for an excellent talk. This is very, very insightful. Well, there's a bunch of sort of thank yous coming in.
Thank you guys for the invitation. It's great to have this opportunity, and I hope to see you all in May, and I look forward to welcoming you all to Philadelphia.
Awesome. Thank you.
Enjoy the rest of the semester. Bye.